Hello and welcome to IFT ZK call. Today, Marvin is presenting the Greyhound, which is a lattice-based polynomial commitment scheme. Yeah, Marvin, stage is yours.
Great. So this is a requested, topic, and to talk about lattice-based polynomial commitment schemes. And Greyhound is, I believe, the newest one. I will apologize if there's a paper that came out like within the last 2 weeks, but this, to my knowledge, is the newest one. So, very brief introduction to polynomial commitment schemes. So a polynomial commitment is a method for essentially giving a compressed form of a polynomial. So a polynomial of, say, degree D has D plus 1 coefficients, and we can compress all those scalars down to, maybe like a single group element in the case of like the first polynomial commitment scheme like KZG. And it's not only is it a compression of it, but it's also a way to bind that polynomial to that representation. So kind of like a hash function binds the input because of the inability to try finding a preimage. Well, not preimage, but collisions. And another convenient property of polynomial commitments are often the hiding portion of it as well, which would be the preimage example for hash functions. Now, the reason you might want to, again, commit to a polynomial is because you need to evaluate this polynomial either through the fact that you don't want the polynomial to be known, or to kind of reduce communication. So if this is the case, you might still need to evaluate those polynomials. So those are used heavily in ZK snarks, such as Plonk. And polynomial commitment schemes that you are more likely to have heard of are ones like KZG and IPA. KZG is used heavily in Plonk and Sonic, and IPA is used for like Halo 2 and bulletproofs. Pondering whether bulletproofs would be would use actually a polynomial as a polynomial commitment, but I'm going to question that for the moment. Anyway, the problem with those two is that they kind of rely on these group theoretic assumptions, and more in particularly, they're assuming that you don't know the relationship between your group elements that are used to form this compression. So that automatically makes it not post-quantum secure. If you would like more information about KZG or IPA as polynomial commitment schemes, please request it as a topic. Okay, now that that's out of the way, Greyhound doesn't rely on these group theoretic assumptions, and instead relies on a lattice-based assumption. And the lattice-based assumptions seem to be a good direction to go through because NIST, a lot of their candidates are lattice-based, so hopefully post-quantum secure. So why should we care about Greyhound? Well, as mentioned, it's plausible that it's post-quantum secure. Okay, that's a good reason. It also doesn't require a trusted setup. Something like KZG does require a trusted setup, which is, really downside, but there's been workarounds for some of those, but not having a trusted setup is fantastic. It also has a polylog proof size. That's pretty good. That's at least the kind of one of those first steps where it's like, okay, this might be practical to use. The verification time is sublinear. That's fantastic. And the proving time is linear. That's, pretty good. So it has a lot of desirable properties. Now, how does it kind of compare from other hash functions? Well, not other hash functions, other polynomial commitment schemes. And this table, I will go ahead and say, is pulled directly from the Greyhound paper. Now, you can see that there's a few other lattice-based cryptography polynomial commitment schemes. So this is not the only one. But if you look at the proof sizes, and these are all in kilobytes, you'll see that these are not really good sizes compared to, the Greyhound one. And the one that's certainly used, probably the most common, would be FRI, which is, again, not a lattice-based, but a hash-based one. So, again, post-quantum secure. And it's for size of n equal to 2 to 26, gives a much bigger proof. So this seems like a good alternative. All right. So the first natural question whenever talking about polynomial commitments is, well, other than what the properties are, is, okay, we have an assumption that we have to make. What assumption theoretically do we rely on? And this is the module SIS assumption. And all we're worried about is that for a given set of parameters, is this probability low? Basically, if we generate some matrix of polynomials in this ring, will a probabilistic polynomial time adversary be able to produce some vector z in which the product is the zero vector, where z is bounded? We want that probability to be negligible. Okay. Any questions so far? This just seemed like a very natural time to ask if there's questions. Not that this is going to be on test or heavily mentioned again. Okay. So now for the rest of the talk, we're going to kind of look at what overall tools are used for the Greyhound polynomial commitment. We're not going to worry about going through all the math or the proofs to see that it's weakly binding and that, if you mess with it enough, you can make it honest, zero knowledge, honest verifier, zero knowledge. But we're going to try having it so that if you walk away from this, you'll kind of know the outline of what steps to take. So that's the goal. And it relies on a property from the Labrador paper that is inner commitments and outer commitments. So if I have a matrix S, and we'll talk about what that matrix S will be in terms of the polynomials we're looking at later. But if we have a matrix S, the inner commitments is just going to be A times S1 and all the way up to T times ASR. And that's going to be the inner commitment of the matrix S by the matrix A. So each of the columns times A. All right. The outer commitments are computed in a slightly different way. Well, completely different way. So we're going to take these inner commitments TI, and the first thing we're going to do is we're actually going to decompose them on some base. So for the sanity's sake, just assume that the vector tilde ti, each entry of that is going to be a binary decomposition. So we're stretching that out essentially to get binary decomposition. And we're going to multiply these together. All right. And that gives us a resulting vector u. And that resulting vector is the outer commitment. Any questions now? I know I just asked that, but this page kind of had a lot of information.
So what is A again?
A is just some matrix that we're going to do our intercommitments based on. Same with B. A and B are just some matrix. In fact, when we look at our Greyhound like setup, those are actually randomly selected matrices. So they're just some known matrix of inappropriate size. In terms of like, do they need to be symmetric or anything? We don't need to worry about that.
But these are public matrices.
They are public matrices, absolutely.
Okay.
Yes. But yeah, but the main thing is, you can kind of think about this as the intercommitment of S by A, and this probably should be like the outer commitment vector U, the outer commitment of S by B or something like that. Just to hammer it even more clearly. But they are public matrices. Okay. So one of the key ideas that is going to be kind of implicitly used in the construction of Greyhound, which we're getting very, very close to, is that a bivariate polynomial can be written as this, where, that's clearly what a bivariate polynomial looks like, where you have a coefficient times some power of x times some power of y over this double sum. And if you view it that way, we can, kind of factor out this xi and have it be the sum of xi times another sum. And that is just a matrix equation. And that's kind of one of the key ideas. Now, one thing to keep in mind is that Greyhound is a univariate polynomial scheme, but viewing it this way, you can make some modifications to make Greyhound work for bivariate polynomials in a fairly straightforward manner. So, but this kind of idea is going to be implicitly used. All right. So let's kind of go through some of the algorithms for the Greyhound commitment scheme. The first one is setup. As we mentioned, the setup requires no trust whatsoever to construct it. So if I want to commit to a polynomial with degree at most n, and we're going to use these kind of parameters MRD, which will kind of determine the sizes of the matrix A and B, then we can, kind of more clearly say what A and B are. But A and B are just, and D for that matter, are just matrices where each entry is a polynomial from this ring. And the A is going to be used for the inner commitment. B is going to be used for the outer commitment. And D we're going to use later on for the evaluation protocol. Now, before Muhammad asked, what is N? N doesn't seem to have a required size. I couldn't quite find where N is fully determined. It's just kind of one of those things that it lines up with the multiplication it might be more apparent going through the nuts and bolts as I write a more detailed description of this. But for the purposes of right this moment, N is not as important as MRD. Those are the parameters that really matter. N is just, it really seems like it could be almost anything, which, if it could be almost anything, there's probably a good reason to not pick a super small N. But all three, the main thing is that all three of these matrices are public and they are randomly selected. Which is kind of the best kind of setup. You don't really have to worry about this the relationship. I did not see disclaimers about poorly constructed matrices being a problem either. But again, things I will keep in mind when I'm writing the more detailed notes. But kind of a very nice setup. All right. So now that we have our setup, we have the matrices A and B. The next question is, okay, how do I commit to a polynomial? So if I have a polynomial f, how do we actually commit to it? And what we do is essentially in 3 steps. We're going to, and these 3 steps are kind of what we're going to have in our heads. I will go ahead and tell you, these vectors f is very natural to go, what are these vectors f? And we'll see them on the next slide. But again, this is just the broad overview of what we're going to do. We're going to construct our vectors of m length over our ring. And then we're going to use these vectors to compute our inner commitments. And once we have our inner commitments, we'll compute our outer commitments. And once we have that, I thought I had another line on this one, which I save for later. But once we have that, then the commitment to our polynomial f will be our outer commitment. We'll also have kind of a witness to our commitment, but we'll see that later on. But the vector u will ultimately be the whole commitment to our polynomial f over this Greyhound's commitment scheme. All right. So let's look at kind of how we get these vectors. All right. So if I have a polynomial and I write it in this way, and this is kind of the way that I mentioned earlier about making that matrix multiplication very clear by factoring out this x to the ID, essentially. Now it becomes, we have these polynomials inside, and those are going to be these polynomials f sub I. And now we're going to essentially take these polynomials and go, okay, now that I have these polynomials, I'm going to work on constructing a vector fi of those polynomials. So I have n over d of them. And remember, n was n equals to d times m times r. So I essentially just have r m of these. And now that I go further and break these up by the m's, I will have just f of them. So that's how we get our vectors fi that I will be doing the inner commitments to. All right. So once we have our inner commitments, we just very quickly, we decompose FIs to get our SIs, and we're going to compute the TIs. The TIs is what we really, well, the tilde TIs are what we really wanted. Those are the decompositions. One of the unsatisfactory portions about this slide from a math perspective is going, okay, what do you mean by decomposition? Well, the SIs and TIs can actually be composed from different bases. And I want to kind of, again, keep this as high level as possible for the sake of, seeing what's going on. So we're going to decompose those, and then we're going to compute our outer commitment. There's a question?
Yeah, so once you decompose FIs into SIs, for example, you get the same number of elements or more or less?
Okay, so what's going to happen is when you decompose those, the decomposition can extend it can make it larger, like the vector larger in terms of I'm trying to phrase this correctly. So the tricky thing about the decomposition is if I do this decomposition, my prime number is Q that we're of our field. And if I look at this in terms of base 2, for instance, then that's, going to be the floor of log base 2 of Q. But if I end up decomposing this with a base of like 5, that's going to give me a different expansion, essentially, size. So you have fewer elements. So that's the so these decompositions for like FI and the TIs, they're going to be different sizes essentially in terms of the vector size. Does that make sense?
Yes, thanks.
Okay. And if there, and like I said, since you'll be one of the ones presumably going through the more technical math details, if there's a particular part that you really want to see the math of, just send me a message after as well. But anything that you feel like is a good question now, certainly ask. So yeah, we construct our outer commitment and we get U. Once we have our U, that, like I said, is going to be the published commitment. The prover should maintain these 2R vectors, SI and TI, the tilde. The reason that the prover should maintain these is because they will be used in the evaluation proof. Obviously, the prover could recompute these, but depending on the storage versus computation, might be better to store them long term. Anyway, so evaluation is going to be the part where we even more hand wave, unfortunately. And the reason this is going to be a little bit more hand wavy is because I did not want to overload the math when it came to decomposition. So in the evaluation, as I mentioned, this is the part where a verifier user has this polynomial. It is known it might be related to a particular circuit, and the point in that polynomial needs to be evaluated at a given point. So the prover is going to basically provide the evaluation at that point X, say Y, and you can have an interactive protocol where the verifier produces the sample vector, or in practical settings, you replace the verifier's challenge with fiat shamir hash, and you're good to go. This is going to follow a Sigma protocol for the most part. So if you're familiar with Sigma protocols, we're going to see a commitment, not the commitment U, if you're not, but the commitment, say V in this particular instance, a challenge and response. Once you have a response, there's going to be something that the verifier has to check. And that's going to be the structure of this. And that's what we're going to see now. It's just these first three steps are going to be kind of that weird part. So the prover is going to compute this strange vector, W, and then W tilde, where W tilde is that decomposition with one of the bases we had earlier. And these bases will be public. The next thing the prover will do is we'll use that other public parameter matrix from our setup, D. We didn't use that for the commitment, but we're going to use it now. And what D is going to do is it's going to get multiplied by W tilde, and that's going to give us our vector V. So let's see what vector V is. Vector V does two things. One, it kind of fixes that X value in place for some of the terms, since that's, in that decomposition. And it also, those Fs are from our original polynomial that was in our computations earlier. So we're kind of fixing our polynomial again with V and our value. And the next thing we're going to do is have the verifier sample a challenge C. In that challenge C, just pick it uniformly random, and our response will be just kind of the natural matrix multiplication of our SIs times C. The SIs are computed exactly the same way as we did earlier, which is, kind of as we mentioned, the prover has these witness commitments. So that's why the SIs need to be maintained, because you had to go through a lot of computations to essentially get those. So we're using them now to do this response vector Z. Now the prover is going to send the W tilde and the T tilde at this point, which is kind of a strange thing that W tilde even gets sent at all, but they're both sent now, which really means, I guess, T tilde could have just been public all along. I'm not sure if there's a good reason it's not, or if there's a fiat shamir reason for it. But there's that. And the verifier is going to have to check two conditions. We'll start with this bottom one first. The verifier is going to make sure that it's smaller than a certain bound. And it's going to be in terms of our various parameters. B1 and B0 are those bases for decomposition that we kind of ignored. And kappa is another one we kind of just ignored. R, D, and M were used for determining our upper bound that our matrix can be. Oh, well, there's N. Yeah, I forgot about N being there. N was the size that I mentioned. I wasn't quite sure where it was used. So that affects the bound that you're able to even do. So that's why you might want it larger. And delta was the log of K, not K, of Q. Now, we have this lovely matrix multiplication. Like I said, I wanted to give you a high level, and then on the last slide, I give you this matrix multiplication. It's not as bad as it looks, though. So what's this matrix multiplication doing? The first row with this is giving us just an equation that checks that V was computed correctly, because V is literally supposed to be D times W tilde. That's what we get. The second is literally computing that the outer commitment is computed correctly as well. So these first two are just verifying that these values were honestly computed. And this third line, this third row, we multiply this out, it looks weird as it's written, but it's literally just going to be showing that your polynomial evaluated at x is y. That's all it is. The vector b I didn't talk about, but there was no way to kind of remove it from this. But it's essentially a bunch of powers of a vector of a bunch of powers of x that kind of fills in the rest of your matrix multiplication for polynomial evaluation identity. So that just verifies that y was correctly computed. And then the last two essentially, again, checks that these values are correctly computed using your challenge. Again, they're just kind of verifying that everything was done the way that we claimed it was. They look that matrix equation makes it look way worse than it really is, but it's just a check. Anyway, like I said, that this is just a very high level overview of, again, how you would go about doing this. So if you were to read the paper or read the notes later, you have a very clear understanding. These checks can actually be, and the complexities that I provided earlier assumes that these checks were done with Labrador. Labrador is another paper that this kind of builds off of, and where the polynomial, the inner commitments and outer commitments come from. But when you have these checks can then be done with Labrador, gives you those complexities, and it just requires a little bit more to do. Not too bad. But I wanted to, again, make this as friendly as possible. Any questions?
Is there any, does it satisfy the homomorphic features like KZG?
So I haven't actually gotten a chance to write like that down, because that is actually a question that I will. I'm going to say I haven't verified this. I believe it should. I didn't see that explicitly mentioned in the paper, but I may have, I'm not above missing stuff. But intuitively to me, because we're looking at, matrix multiplication and matrix addition, I kind of feel like it should. So intuitively, I want it to satisfy the homomorphic properties, and but I don't actually have a good answer whether it does or doesn't. I believe it does, but I can also be very certainly wrong, because I could see something weird happening with the decomposition, or well, the decomposition should be fine. But I could see something weird happening during. See, I want something weird to happen and break this, but because matrix multiplication distributes over matrix addition, it shouldn't. So I think I'm being paranoid, but I feel like it should be homomorphic. I just don't like saying definitive statements without, verifying and proving it first.
Oh, it's okay. Yeah.
Um,
Do
but
they
I'm-
mention it if it's homomorphic or not in the paper?
I don't remember seeing that, and I did glance through to try finding that, but there were a couple of sections that I didn't read as thoroughly, because while preparing this talk, I wasn't as concerned about double checking their proofs of completeness, because I know they're going to be correct. There's certainly things I will, check, when I'm writing the notes up for Codex, but things like that is like, okay, I know this is complete because of how you've structured it. So it may have been like, one of those hidden sentences in there going, oh, by the way. But mathematically, nothing I see should prevent it from being homomorphic. And if it's homomorphic, that would make it really valuable for, Codex or really any good application. There was another thing that I will mention, and I'm trying to remember exactly where I saw it, because I'm not sure if it made it into the slides, but there is an idea from Labrador that they show that R1CS reduces to. So yeah, it did not formally make it into the slides, but it's the dot product relation, and I think that was Labrador that may have
Yeah,
had
thank
that.
you.
But anyway, other questions?
So aside from being, let's say, quantum skewer, does it provide any like efficiency or improvement in performance, at least in some scenarios, over like, let's say, KZG or other polynomial commitment schemes?
I mean, the obvious thing to say when you list off KZG is go, there's no trusted setup. But but in terms of, I mean, KZG is obviously proof size is way better, verification time, complexity is constant. Now I don't know how long it takes to run a bilinear pairing off the top of my head, but there's certainly potentially like sizes of n where this could beat it, but whether those are practical, I don't know. But I feel like whenever you're adding more and more, well, not adding, but kind of removing some of the stuff, that you're going to lose some of the advantages that were built up over the years with the group theoretic methods. So I think that the big reason to care about this is that it's post quantum, and as I mentioned, it does have reasonable complexities. The assumptions fairly nice. If you look at some of the assumptions for other schemes, you kind of get into other more recent schemes. You kind of get some of these crazier ones that are a lot harder to get intuition of what they even mean. So from a just purely approachable level, that kind of makes Greyhound a little bit more desirable, but I mean, that's not a good math reason to like something. But I don't think there's. I would be surprised if this beat KZG in any way other than post quantum and trusted setup. I'm very happy if someone shows me I'm wrong, or very happy if I discover I'm wrong, later on. But
It seems to be popular for like folding schemes. From what I I have read, it improves performance for specifically for folding, but I'm not also sure
I could see
how
that
much.
because you're dealing with more matrix multiplication, so you don't have this intermediate operation where you have to go to groups. I could kind of see that, but so if you can send me any of those readings that you may have seen with like Greyhound and folding schemes, I would be happy to look at that too.
Yeah, sure.
Because most of my ZK readings comes from ePrints. So I'm always happy to, absorb any non papers or more papers that come from different sources. Other questions?
I have no questions by a comment, and the Starks are really faster than Snarks, if we can have two different categories, Snarks and Starks. And one of the biggest criticism to the Starks is about the proof size, right?
Yes.
And since this Greyhound is reducing the proof size dramatically than the others, yeah, I think it's very valuable. Of course, it requires some relax from the proving time, maybe, but still, it's a good example. Thank you.
And as you mentioned, the distinction between Starks and Snarks at this point are basically Starkware does Starks. It's I think it's gotten to that point where in the vernacular that people have just decided that Starks are Snarks, and I mean that's the latest I've seen, at least. But using FRI, like you said, you can even see here that the proof sizes are vastly different. So that could be a potentially an interesting direction if somebody like Plonky 4 adopted Greyhound, or maybe even better lattice-based scheme. All right. So I think that's all the questions.
Yeah, I think there's no questions, and maybe we can wrap up. Thank you, Marvin, for presenting, and thank you for thank you auditors to listen this and contribute. And yeah, see you in the next presentations.